In this video, I will introduce you to the concept of tensors. What is a tensor? Wikipedia has a page that defines what a tensor is. It says, in mathematics, a tensor is an algebraic object that describes a multilinear relationship between sets of algebraic objects related to a vector space. Well, so what is an algebraic object? What is a vector space? This sounds too abstract if you do not already know what tensors are. So, let's look at examples of tensors and intuitively understand what they are. This is a 2 by 3 matrix. It has 2 rows and 3 columns. A value in the matrix can be located by row and column. For example, the value at the first row and the second column is 2. In short, a matrix has 2 axes. We also say a matrix has 2 dimensions. And a matrix is a tensor. Specifically, it's a 2D tensor because it has 2 dimensions. Let's introduce a more concise notation to represent a value in a 2D tensor. We'll call the 2D tensor as m, and use zero-based indexing for both axes. So the value at m01 is again 2. How about m12? It's 6. How about m0? It's the first row of the 2D tensor. When specifying only the first axis, it returns all values from the remaining axis. So, m0 gives us a list of values. It's a vector containing 1, 2, and 3. And a vector is also a tensor. Specifically, it's a 1D tensor because it has only one dimension. So far, it makes logical sense. A matrix is a 2D tensor, and a vector is a 1D tensor. Following the same logic, a single value, or what we call a scalar, is a 0D tensor. However, we'd often use the terms scalar, vector, and matrix than 0D, 1D, or 2D tensors. Yet, we've discussed the low-dimensional tensor examples because it's easier to understand what they are. Now, we are ready to venture into higher-dimensional tensors like 3D and 4D tensors with more realistic examples. This is an image of a seaside city with skyscrapers. It looks nice. But let's put the beauty aside. We'll analyze the image as a data structure. A digital image is a rectangular tiling of pixels. Pixel is short for picture element and is the smallest unit of a digital image. We can locate a pixel on an image by its row and column positions. This may sound similar to the 2D tensor structure. However, we need more than 2 dimensions. As we are looking at an RGB image, each pixel has the intensity of red, green, and blue. For example, the values of a pixel may be 128, 94, and 32. Again, those 3 values indicate the intensity of red, green, and blue, respectively. The intensities range from 0 to 255. 0 means no color, and 255 indicates the highest intensity level. As such, each color has 256 possible intensity values. Therefore, a pixel in an RGB image can represent 256 by 256 by 256 colors, which means a lot of colors. Well, 16,777,216 different colors to be exact. We want to know how to represent the RGB image as a tensor. Let's call it G. We know that if we specify the location of a pixel, we get 3 values, a vector of RGB color intensities. A vector is 1D tensor. To obtain a value from it requires another axis value. For example, G480, 180, 0 gives the red color intensity of the pixel, which is 128. Similarly, we can obtain the green and blue color intensities using the third axis. We'll call the third axis a channel. So, we specify the row, column, and channel positions to retrieve a color intensity value. As we have seen, we can represent an RGB image as a 3D tensor, where the last axis defines the color channel. So, the order we access a color intensity value is by row, column, and channel. Since we accessed the color channel last, we call this representation channel last. We can also access the same point in the 3D space by selecting the channel first and then row and column. We call such a representation channel first. The first axis is the color channel in this representation, and the remaining axes are for rows and columns. So, which should we use, channel first or channel last? It depends on your library's memory format and what the underlying device uses to store and process tensors. Suppose we have a 2x2 RGB image. There are 3 color intensities for each pixel. In channel first memory format, values in each channel are contiguous. Therefore, we can access each channel's color intensity values sequentially in memory. For example, color intensity values are laid out for the red color channel first. Then, the green color channel. And the blue color channel. Whereas, in channel last memory format, color intensity values for each pixel are stored together. Therefore, we can access each pixel and its color intensity values sequentially in memory. So, color intensity values are laid out for the first pixel first. Then, the second pixel. The third pixel. Finally, the fourth pixel. In machine learning, we often process multiple images simultaneously rather than one image at a time. We use a 4D tensor that combines images into one batch. The first image is indexed at 0, the second one at 1, and so on. Let's call the 4D tensor K. The first image is K0, which is a 3D tensor. The second image is K1, which is again a 3D tensor. You got the idea. Let's say we use channel first representation of RGB images. In the 4D tensor, K, we can drill into a pixel color intensity level by going through the dimensions. We start with the image, channel, row, and column positions. For example, image 1 for the second image. Channel 2 for the blue color channel. Row 120. And column 98 for the location. And we have a blue color intensity value. This concludes the introduction to tensors. I hope you are feeling comfortable with the concepts. Bye for now.